Morning, everyone. My name is Jim Gardner. I'm one of the research scientists here at the museum. I'd like to welcome everyone on this fine, frosty morning to talk about the Arctic. And today we'll be listening to Dr. Jaelyn Eberle from the University of Colorado in Boulder. Jaelyn grew up on the Saskatchewan prairies, where she spent her summer collecting rocks and fossils with her grandmother, and by the age of 5, knew she wanted to be a paleontologist. In 1991, she completed her undergraduate degree in the paleobiology program at the University of Saskatchewan and moved south to do her graduate work, earning a PhD at the University of Wyoming with Jason Lillegraven. And her PhD work there focused on the KPG boundary, which is the boundary that marked the extinction of the dinosaurs about 66 million years ago and the subsequent flourishing of mammals in the Cenozoic. And I believe Jaelyn also coined the infamous term zone of uncertainty during her work there. Subsequently, she did postdoc work at Rice University in Houston and a couple of stints as curators at the Houston Museum of Natural History and back home in Canada at the Canadian Museum of Nature in Ottawa. In 2002, she returned to the Rockies, and where she became curator of fossil vertebrates at the University of Colorado Museum and a professor in geological sciences at the University of Colorado. And Jaelyn lives in Broomfield outside of Boulder with her husband David, who's a geologist, 3 sons and 2 dogs. And as a nod to her Canadian heritage, I learned last night one of those dogs is named Finnegan, after, of course, the puppet whose mouth moves, but he doesn't speak, on Mr. Dressup. Jaelyn's research concentrates on the study of mammals during past intervals of climatic change, particularly the early Eocene greenhouse world, and the recovery and evolution of mammals following the KPG boundary mass extinction. Her research also involves analyzing the oxygen and carbon isotope ratios in vertebrate bones and teeth to quantify Arctic paleoclimates and provide some insights into the paleobiology of ancient Arctic mammals. So, for example, looking at aspects of their diet and behavior. And her fieldwork ranges from the Rocky Mountain regions north into the North Slope of Alaska and Canadian High Arctic. And today she will focus her talk on some of that work she has been doing in the Canadian Arctic. So, Jaelyn?
Okay. Can everybody hear me okay? Okay. And the lights stay about like this? They'll go down. Okay, great. Okay, well, thank you very much for being here and for inviting me to come up to Canada and give a talk. As Jim was saying, I grew up in Saskatchewan. I grew up on the prairies, but I've been in the Rockies now for about 15 years or so. So I'm going to talk about life at the top of the Greenhouse Eocene world. Now, the Eocene is an epoch. It's a time interval. And what I'm going to show you today is what we know about the early Eocene, so about 52 to 53 million years ago in the Arctic. And I've been going up to the Arctic since I postdoced with a couple of paleontologists that started up there, Mary Dawson, Malcolm McKenna. And I started postdocing in the late 90s with those folks, as well as with a paleobotanist out of Saskatchewan, Jim Bassinger. And I've been kind of going up off and on ever since. And so I want to talk to you a little bit about what we now know about the early Eocene Arctic. I work mostly on the fossil mammals, but I've got a number of colleagues that I work with who work on fossil plants. And so I'm going to talk a little bit about that as well, so you get a better view, kind of a more rounded view of the environment up there. Okay, let me make sure this works okay. Oh, there we go. Perfect. So where we're going to go today, a geographic focus of my talk is going to be kind of a couple places. I'm going to talk a bit about, or a fair amount about, Ellesmere Island and Axel Heiberg. And then I'll also talk about Banks Island, which is Canada's westernmost Arctic island. Now, this inset here is of Ellesmere and Axel Heiberg Islands, and that's where most of the fossil vertebrates that are Eocene in age come from in the high Arctic. That star here is where we'll spend most of our time today, in the Bay and Strathcona Fjord area. But I just want to point out there's also vertebrates down here on southern Ellesmere Island, and over at Geodatic Hills and at Molka Fjord, which I'm not going to get into today, but certainly if folks have questions, I'm happy to answer them. So there's also a few other names on here. Brainerd's Fossil Forest up there, Hot Weather Creek. There are a number of fossil plant localities. And in fact, the fossil plants that are Eocene in age, some of those discoveries date back to the Greeley expedition. And in fact, Captain Brainerd was one of the 6 survivors of the Greeley expedition. And that fossil forest was named after him up there. Fossil vertebrates, Eocene fossil vertebrates, are relatively recent discoveries to the Arctic. Mary Dawson discovered the first ones in the mid-1970s, and in fact, the world saw its first Arctic alligators, albeit fossil forms, in 1976. Realized that by that time, 1970s, it had been a century earlier that fossil mammals of that same age were being discovered at mid-latitudes, say in Wyoming and Colorado. And so enough of our work in the Arctic has been on describing fossils, simply because we haven't had that century of discoveries that folks in the mid-latitudes in Wyoming and Colorado have had. Fossil vertebrates in the Arctic are fairly recent, or at least Eocene ones are fairly recent discoveries. Okay, so where are we going to go? Oop, maybe I'm not facing the right way. There we go. So why do paleontology in the Eocene rocks of the Canadian Arctic? Well, this is what it looked like in 2004 when we first started work on Banks Island. This was the 4th of July, actually, so it looks like Christmas. But in any case, the Eocene was unlike the Arctic today. The Eocene marked the height, the early Eocene marked the height of global warmth since the dinosaurs went extinct. The dinosaurs went extinct 66 million years ago. So at between 50 and 55 million years ago, we had this height of global warmth. It was a fairly warm Earth. And so the early Eocene is a deep time analog for understanding a mild temperate Arctic that doesn't have permanent ice. The doomsday studies right now would suggest the Arctic will be without permanent ice by the year 2040. That's the estimate on the street right now. And so trying to understand what may be in store for the Arctic, one way to do that is to look at these past intervals of global warmth. So also, by looking at the early Eocene Arctic, it allows us to understand species adaptations to the polar light regime, and I do a fair amount of work on that. I'll talk a little bit about that today, although I'll spend some time talking about a couple other points here as well. The Arctic, when you think about where the Arctic is, in the early Eocene, the Arctic was en route to basically for dispersal of species coming from Asia into North America across the Bering Land Bridge, but also coming from Europe into North America across what's called the Tulian Land Bridge. And so there was a fair amount of dispersal, especially in that very early Eocene time, and we see evidence in the high Arctic because we see animals there that also occur in Europe and also live in Asia at that same time. So that's another way reason to study the Arctic. And then what I'm going to talk a little bit about is the Eocene Arctic fauna tells us a bit about the Arctic Ocean during the early Eocene time, and I'll just say it's a little different than the Arctic Ocean is today. And here I'm going to talk a little bit about sharks. So most of my work is fossil mammals, like what Jim said, but now and then I deviate and I need a new critter to work on, and I've been working a bit now on fossil sharks. So I'll talk a bit about those as well. Okay, so here's an outline of my talk. First of all, I'm just going to talk a little bit about mammalian paleontology. I'll give you a geologic setting and show you where the Arctic was in the Eocene. I'll talk about climate and how we get at climate in the early Eocene. Then I'll talk about the mammals and the floral diversity and the composition. And then finally, time permitting, we'll talk a little bit about the marine vertebrates. Okay, I'm sure we've got some folks out there who speak French, and I will try to pronounce this right, but montrez-moi vos dents et je vous dirai qui vous êtes. This was spoken by Georges Cuvier, a fairly famous mammalian paleontologist in the early 1820s. What does it mean, you guys? Absolutely. Show me your teeth, and I will tell you who you are. This is my dog, Rocket, when he was a puppy, and you can see those beautiful chompers in there. Mammals are really interesting from this perspective. First of all, teeth are the hardest part of your body, so they're the most likely part of you to become a fossil. Importantly, fossil mammal teeth are highly diagnostic, and meaning you can identify a mammal down to genus and even species by looking at its teeth, particularly these teeth here, what are called the cheek teeth, the premolars and the molars. So that's great for folks who work on fossil mammals. Ideally, you're going to find a lot of teeth because they're more likely in the fossil record, and importantly, you can identify them based just on those teeth. So mammalian paleontology is primarily about teeth. People sometimes refer to me as a paleodontist, although my patients don't scream when I study them and poke them with, dental tools. And teeth are the most abundant vertebrate fossils. In fact, the most abundant one, I believe, is shark teeth. Recent fossil mammals are identified on their teeth. And then after the Cretaceous-Paleogene boundary, which is where I spent my PhD work, mammals evolved fairly rapidly, and we can see that in changes in their teeth. What you're looking at over here is a little jaw. That's a millimeter scale, so that's a lower jaw of an early mole. It's probably among the oldest of the North American moles that we found in Colorado up at Florissant. And simply by looking at those teeth, the patterns of the bumps, which are the cusps, the ridges, which are the lofts, and those valleys or basins, you can get an idea of who you're dealing with. What is this genus and what is this species? Okay, and I should point out the Arctic has a fair amount of teeth. So you're going to see a lot of mammal teeth in my talk today. It's got a lot, and that's certainly one of the reasons that I initially wanted to work in the north. Is not only is it an interesting time interval, the early Eocene, to be working in the Arctic, but also mammal teeth. They first started coming out in the mid-1970s with the work of Mary Dawson, and I started work when I was a postdoc in the late 90s, and have just continued that work. Okay, so this is a map by Dave Eberle, loaned me this, who's out there. And this is where we're going to go today. We're going to spend most of our time between Strathcona and Bay Fjords. This is about 79 degrees 45 minutes north latitude. And now what I'm going to do is I'm just going to zoom in on that area and show you an aerial view of what this looks like. So this is the area. It's a beautiful place. And where the fossils are coming out are this unit right through here. This is called the Margaret Formation. It's a little over 1,100 meters thick. It was measured by Dave Eberle, who's out there. And it's made up of sandstones, siltstones, mudstones, and even some coals. And what you're seeing here, this is a thick coal. Oh, is that? Let me see if I can twist that. Sorry about that. Hopefully I'll keep it from moving too much. So that's a thick coal, and in fact both Canada and the United States have proposed open pit coal mines for the Arctic, but thus far it has not occurred, but that was one of them that they were particularly interested in. Our camp, you can see a little dot there, that's one of the tents. Does anybody know what these reddish rocks might be? They're not shale, but that's a good guess. They're clinker. So when coal lights on fire, if you light coal on fire, say with a lightning strike, you can get clinker, and it's this bright red. You're going to see a picture later in my talk. We call this Clinker Airport because what the planes would do when they'd land us, we'd fly up on a twin otter. They would basically land and essentially park at one end, we'd unload all of our stuff, and then when they'd take off, you can see that one side is steeper than the other. They would start over here, take off, and you better hope he's off the ground by the time you hit the other side. I don't know how many times we're going, please, please get off the ground. So he just had a nice landing strip, so you'll see our airport shortly. So anyways, this is where our fossils are coming out. What I want to do now is show you a geologic map of what these rocks look like on a geologic map, and an air photo that'll show you where our sections went through, some of the early sections. Okay, so this is a geologic map done by Chris Harrison of the Geological Survey of Canada here in the Calgary office. And this light yellow unit is called the Margaret Formation of the Eureka Sound Group. A group is made up of a number of formations, and the one we're interested in with those early Eocene fossil vertebrates is the Margaret. And this here is where we were kind of looking from the helicopter, and you could see those beds wrapping around. They call this Matthew Syncline, named for William Diller Matthew, who's a Canadian paleontologist, mostly working in the late 1800s, early 1900s. But in any case, you'll see lines through here and numbers and names. Those are all localities, and those are some of the early strat sections that were measured through this area. Okay, so now we'll look a little bit at these strat sections. So this is a strat section that was published a couple years ago by Dave Eberle, who's out there, and myself. And what you're looking at here, so a strat section is when you measure the thickness of the rock. You're going to measure, in this case, 2,200 meters of thickness, and you're going to tie in the fossil localities, so you know what the age, the relative ages of the fossils are relative to other localities. Okay. And so that's what we did. Dave came up with us in 2010 and was measuring sections while we were happily collecting fossils, which is a great way to have it. And what I will say, the fossils they were collected initially discovered by Mary Dawson, Malcolm McKenna, Howard Hutchison, and others, but the stratigraphic sections hadn't really been published. So that's one reason we took Dave up with us, is to get a really clear-cut view of the strat section and how the fossil localities fit in. And so what we've got up there is the best, most productive part of the section is something that's considered to be late Wasachian in age, or about 52 to 53 million years old. The word Wasachian is a land mammal age. It's a North American land mammal age based upon first, last, and unique occurrences of different mammal species. And I will show you later how biostrat works, but essentially looking at the fossil mammals that are present in the Arctic would give us an indicator that it's about that age. What we have in this lower unit, we have over 25 genera of mammals, including this guy, Coryphodon. You'll see him a little later. He's kind of a hippo-like guy. We have at least 15 genera of reptiles, including alligators. We've got bird genera, including the large flightless Gastornis. It was published maybe a year ago or so. And then we have some fishes as well. So there are a few fishes up there. So there's this section, and that's where most of the fossils have been collected since the mid-70s on forward. But then you've got a gap of almost 500 meters, and then you've got this upper unit or upper section that contains fossils, all within the same Margaret Formation. And this one's not nearly so diverse. You've just got a couple different kinds of mammals, reptiles, including alligators, and then a single bird, a wading bird. So I'm going to spend most of my time talking about this because that's where most of the work has been done. That's where the most productive localities are in the Eocene Arctic. So Eocene paleogeography. So where was Ellesmere in the early Eocene? You might look at this map. This was created by Ron Blakey at Northern Arizona University, and you might look at it and go, well, you know, it doesn't look awfully different from today. There are a few changes. You're going to see a pretty isolated Arctic Ocean. We'll come back to that one. But Ellesmere, what you're going to see is that Ellesmere Island and the fossil sites were well above the Arctic Circle during the early Eocene. So 50 to 55 million years ago, Ellesmere was way up there. What does that mean? Well, what it means is that your animals and your plants that lived up there in the early Eocene are dealing with the same light and dark conditions that we have today up there. When you're above the Arctic Circle, you've got 24 hours of sunlight for months, and you've got 24 hours of darkness, months in the winter. So these animals and plants would have had to be dealing with that special Arctic light regime. So just keep that in mind as we go through. Okay, paleoclimate, how does this all work? Well, it's been used for centuries now, this idea of what we call NLR, or nearest living relative-based methods. When you find an alligator jaw in the Arctic, like this one that was found in 1975 by Mary Dawson, Mac West, and others, when you find something like that, you're going to make the hypothesis. You'll say, well, it must have been fairly warm. What that's based on is when you look at, say, the present-day distribution of alligators, including alligator mississippiensis, which is the guy we have living in the southern United States, and you take a look at that window of where he lives in the United States, you can come up with a climatic estimation based on that geographic window. And this is what folks have come up with. This is the work of Markwick in the 1990s, and he had said, well, you had to have a mean annual temperature of around 16 degrees C in the Arctic, cold month mean had to be above freezing, and a mean annual range of temperature of maybe 20, 21 degrees. And, you know, this stayed quite acceptable for quite some time. And, you know, I would put this in talks when I first got to Colorado, and I had a geophysicist come up to me and say, well, how do you know that? How do you know alligators behaved in the Eocene and were physiologically the same as they are today? I mean, maybe alligators, I had one climate modeler say, can't you put hair on your alligators? I mean, you know, because the climate modelers at one point couldn't replicate an environment for the Arctic that the paleontologists were saying was pretty warm. And so I said, well, you know, it's a fair question. We should be able to test independently whether these guys are pretty good indicators of warmth in the Arctic. And so we said, well, okay, let's look at some other proxies. And what I ended up doing is moving a little bit into geochemistry, into stable isotope geochemistry. And I'll say this is a new field. This was a new field for me about 10 years ago, but I'm getting a little more comfortable in it now. And basically, how stable isotopes work, particularly oxygen. I won't deal with the others today, but we'll deal with oxygen. Oxygen isotope ratios that are in vertebrate bones and vertebrate teeth, including your teeth, can be used for estimating paleotemperature. This is how it works. You are what you drink. Animals will take in water whose oxygen isotope ratios are correlating with climate variables, specifically with temperature and with humidity or aridity. How we look at oxygen isotope ratios, what we're looking at for this kind of work is a ratio of O18, the heaviest of the oxygen isotope ratios, to O16, which is the fairly common, abundant one that we have today. We look at that ratio compared with a standard, a lab standard, and everybody's using a consistent lab standard. And by measuring that ratio in teeth or in bone, we can come up with an idea of what the oxygen isotope ratios of the river or the lake these animals were drinking was. And it's that value that correlates with temperature and potentially with humidity. In a super humid environment, it's predominantly correlating with temperature. So that's what we did. The catch is it's not one-to-one. That is, if you sample a tooth of say a zebra, and you measure its delta O18, it's O18 to O16 ratio, it's not going to be one-to-one with the river, but there are a lot of models out there that account for the physiology of different animals, the inputs and outputs of oxygen, that you can actually come up with a temperature estimate by plugging this guy's value into a model. So that's how we're getting at it. So we measure del O18 in his teeth, we relate that to the river, and then the river itself relates to climate. How this works, so this is the model that we happen to use. It looks really simple here, but it's like this super long equation that you can take down to this. But essentially what we do is we use a mass spec. First of all, we take a little dental drill, sample the teeth of these guys, basically do a bunch of chemical treatments to separate out either your phosphate or your carbonate oxygen, and then we plug that into this model to come up with this oxygen 18 value of the river, which we then plug into this down here alongside some fish bone, his appetite, and you can come up with temperature. This is not a new equation, and this isn't an equation that I came up with. This is something that was brought up was developed by Longanelli and Nudi in 1973. So this has been known for some time. But what this can give you then is a mean annual temperature. And when we do that with Mr. Coryphodon, which is a big hippo-like guy, semi-aquatic in the Arctic, you get a mean annual temperature in the Eocene Arctic of about 8 degrees Celsius. And some of you may be saying, well, oh, okay, that's not super warm, is it? Well, it's about minus 19 degrees Celsius at Eureka these days. Probably a little warmer than that now, but for a MAT, for a mean annual rate, or mean annual temperature. You can also work with different kinds of animals. In this case, we worked with turtles. Turtles grow their shell when they're not in the tropics. They grow their shell in the summer, even if they're in temperate regions. And so by sampling turtle bone, plugging it into a turtle model to come up with a delta O18 at the river, we can come up with a warm month mean. And when you do that for the Arctic Eocene turtles, we used pond turtles that Howard Hutchison had identified. You get a warm month mean of about 20 degrees Celsius. So that's a pretty pleasant Arctic temperature for the summers. So how does this look? So this is our data right here in bright yellow that uses the oxygen isotope ratios of bones and teeth. And what you'll find is here we have about an 8-degree MAT. That's this column right here, mean annual temperature. We have a warm month mean of about 19 to 20. And then we have a cold month mean anywhere between 0 and about 3.5. And I didn't point this out, but the mean annual range of temperature, or the MART, is something you can get by taking one of those big tusks of Coryphodon, sampling multiple ones, and kind of lining them up to give you seasonal data. So that's where we can get that range from. And what you'll find is that our data is actually really close to some of the paleofloral analyses. They have an 8.2 degrees C, minus 2 degrees C cold month mean. So you've got plants and oxygen isotopes that are giving you pretty comparable data. And that's what you really like if you're working paleoclimate, is you like to have multiple proxies, multiple tools that are kind of giving you a similar answer. So we felt not too bad about that. Well, what are some biological implications then? Well, one of the things I would say that's important to point out then is that so that initial data that came out in the 1990s, based on entirely nearest living relative-based methods, would have put Ellesmere Island around 15 degrees C for a MAT, and we're taking it considerably lower. We're saying it's about 8 degrees, as are the plants. What it's suggesting to me is that these guys are hardier than perhaps their geographic window indicates today. And I think these kinds of studies where you're independently determining temperature ranges of organisms that lived in the past is a means for us to try and come up with an idea, and maybe to better gauge how organisms today may deal with, say, global climate change. The windows that these guys occupy today, for example, alligators in the southeastern United States, may not be entirely climate. I think it may be people too, as to why that window is the way it is. So certainly their tolerances in the Eocene would seem to suggest that they can tackle a little bit more in terms of temperature, or little cooler temperatures actually, a little hardier. I haven't pointed this guy out here, but we also get giant tortoises in the Arctic, put into geochelone or hadrianus, and big, thick chunks of shell. Again, if you looked at just these guys and where they live today, for example, Galapagos Island, you'd probably put the mean annual temperature much warmer than what our isotopes would suggest. But I think what we would suggest is that these guys were hardier, or could handle cooler temperatures in the Eocene. Okay, so I want to talk a little bit about mammal diversity. What are these guys? Anybody know what those guys are? This is Ellesmere. Muskox, yeah. These are probably the most abundant certainly of the artios that I see up there. When I go up in the Arctic, we always see herds of these guys. And this is central Ellesmere, and that is a bay called Fossil Bay in the background. So this is about 79 degrees, 45 minutes. 78, pardon me, not quite 79. Okay, well, I want to talk about diversity. So the Arctic today is home to maybe a dozen or fewer different species of mammals, and includes some of these guys. This is a Perry's caribou. We've got the muskox in there forming a circle, probably with a baby in the center. Foxes, and of course the Arctic hares that stay bright white in the summer. So you have about a dozen or so species. And what's interesting, though, people have started, certainly zoologists do this pretty regularly, is they look at diversity gradients. They look at, well, okay, how does diversity change from, say, the equator to the poles? And this is a colleague of mine has done some of this work, Christy McCain, and her student. And basically, and this is a diversity map for mammals throughout the world. And what you're going to see, probably not surprisingly to you, is that at the equator you have the highest diversity, anywhere between 190 some and 250 some different species of mammals. But it's a very steep gradient. It goes super steeply down, and you can even see Ellesmere is not even shaded in there, but essentially you're getting, they say 0, but you're never at 0. You've got maybe a dozen, upwards of a dozen species. So from 250 potentially down to a dozen. So we would call that a very steep diversity gradient from the equator to the pole. Now, we don't totally know exactly what is controlling this diversity gradient, but a lot of folks have suggested temperature, humidity, paleoclimate may be involved. Well, one of the things we thought of doing, well, let's look at diversity in the Eocene, where we know we had a shallower climatic gradient, latitudinal climatic gradient, where it was warmer in the Arctic than it is today. So we said, well, okay, do we see that in the diversity as well? Do we see animals have just a shallower diversity gradient, or maybe no gradient at all? And so we started looking at that. So first of all, this big list, you don't need to know who all these guys are, but there are over 25 genera of mammals from the Eocene. So you've got 12 today, over double that during the early Eocene. And some of these groups you probably recognize. There's rodents, there's carnivores, we have those guys living today, primates, we are primates, lots of primates today, and Perissodactyla. This is a group I've spent a lot of time on in the Arctic. The Perissodactyls would be your odd-toed ungulates. So today that includes your horses, your rhinos, and your tapirs. In the Arctic, the early Eocene Arctic, it was mostly a world of tapirs, which is kind of strange as far as Perissodactyls go. And then there's some groups on here that some of you may recognize but are extinct. We don't have them living today. Multituberculata, Craig, I know you know these guys quite well. Pantodonts, Coryphodon, that's that hippo-like guy, kind of the star of the show with the isotopes. And then Creodonts, which are kind of large primitive mammals that are carnivores. I'm going to show you pictures of some of these guys, by the way. So now, if we color the ones in red that we also see in mid-latitude North America, this is why biostratigraphy works. This is why mammal fossils can be used to date the rocks, is because all of these taxa in red occur in mid-latitude North American sediments that have been dated. And then you can go, oh, okay, it's about 52 to 53 million. We do have an ash age on Ellesmere Island. It's on the south, and it's 52 million plus or minus about a million. So it's not a super tight age. But what's interesting is the paleontologists had been saying, yeah, it's late Wasatchian. It's 52 to 53. And then maybe 5 years ago, somebody came out with an ash age, and they said 52 plus or minus 1. And I go, wow, those fossils are pretty good. So they seem to be telling us and working well for date. Okay, I want to show you some of these mammals. So this is a jaw of this guy, Coryphodon. This guy was a hippo-like guy. Probably, some people call him the sheep of the Eocene because they were so abundant in the early Eocene. And you see a number of them in the High Arctic. Their fossils are among the more abundant ones. I'd also say it's probably a collecting bias because they're big. And so if I'm marching across the Arctic, I'm more likely to spot them and some of the other fossils. We also have tapirs. And that's what these are living tapirs. And this is a maxillary. So that's this bone right here for you, side of your face, your cheek. And these are his cheek teeth, his molars, and his premolars. What's really interesting is in the early Eocene mid-latitudes, tapirs are rare. And in fact, tapirs aren't a common fossil, really, at too many time intervals. In the High Arctic, they're abundant. So there were Lots of tapirs in the Eocene Arctic. It's just kind of strange. And then this guy down here is a brontotherium. Most times when people think of brontotheres, they think of the later forms, which are big. Saskatchewan, where I grew up, Cypress Hills area had these great big late Eocene brontotheres, about 34 million years old, and they had these cool horns sticking on them. They kind of look like rhinos, but with a V-shaped horn. Early brontotheres, which appeared in the early Eocene, in fact the Arctic ones are some of the oldest ones, don't have horns and they're about the size of a sheep. So this is how those big guys originated, if you will. So these are some of the early forms. And that's what we have up in the Arctic, mostly teeth, these guys. So in addition to these guys, we also have some of the small guys. So we have primates. This is a plagiomenid, which is a kind of primate. This is a little guy called a paleonodont, Arcticanodon. Some paleontologists have suggested it may be related to a pangolin. Kind of jury's out on that guy. And then this is a molar of a primate as well. What's kind of cool about the Arctic is you've got a lot of different primates, which is kind of strange, and we'll come back to that. The challenge with the Arctic is that you have a lot fewer fossils than what you have at mid-latitudes. And so it can be difficult to try and determine or try and compare diversity in the high Arctic with the diversity in, say, Wyoming and Colorado that have the same aged rocks and the same aged fossils if you've only got 80 specimens at the most productive site in the Arctic and you've got 300 at some of the sites in Wyoming. So that can be difficult to do. And what we did is we did a technique called rarefaction to compare diversity in samples that are of different sizes. And I'll show you how that works. Basically, we compared localities from the Wind River Basin, Green River Basin of Wyoming, and the Huerfano of Colorado. These are the same age, that Wasatchian age, as the Arctic sites. And we wanted to compare them and see how do they compare in diversity. So we did some rarefaction techniques. Let me show you what these look like. This is a curve, a rarefaction curve, and what you do is you read a rarefaction curves, you read it from right to left. This is the Wind River Basin curve. The yellow and the green are the Green River Basin. Purple is Huerfano in Colorado. And then finally red is locality 85 with its 75 to 80 specimens. Well, what you do is if you rarefy these 275 specimens back down to, say, 80, so if we were to subsample that 275 specimens, pull out 80, you would probably get somewhere in the range of about 27 or 28 genera. And I should point out, this is number of specimens on the x, number of genera on the y-axis. And what this suggests is because you see the Arctic curve, that rarefaction curve, kind of in amongst the Green River Formation curves, what it's suggesting is that the diversity in the Arctic, albeit limited in specimens, the diversity would suggest that it's comparable to the Green River Basin in Wyoming at the same time. The Wind River blows everybody away. We don't know why. We don't know why the Wind River Basin was so diverse compared to other early Eocene faunas at the time. But what this is suggesting is that our Arctic fauna is kind of holding its own. It's fairly diverse relative to some of the sites that are fairly well collected at mid-latitudes. So here's where it gets even, to me, gets more fun, and that's when you start looking at the composition. So maybe you've got a good diversity in the Arctic. What you're looking at now, this nice colorful donut, each of these different colors represents a different family of mammal, only from this locality 85, which is our most productive site in the early Eocene Arctic on Ellesmere Island. And what you're going to see is these light green and this green here, those are primates. Over half the fossils from that site are primates. You got some rodents and you got a bunch of tapirs. Just as interesting as kind of who's there, lots of primates, tapirs, is who's missing. And some of the guys that are missing, let me put all these guys up and I'll talk about them. Well, if you work in the early Eocene and mid-latitudes, and in fact my fossil collection in Colorado is filled with these guys, is horses. Horses are super abundant in the early Eocene. We don't have a single horse in the Eocene Arctic. There are a dime a dozen in Wyoming, not a single horse up there. Hyopsidas, this is a little primitive, kind of a rat-like guy. They're called an archaic ungulate, meaning a primitive, potentially an ancestor to later ungulates, Hyopsidas. Many fossil localities in Wyoming over half the fossils belong to that guy. None of them in the Arctic. And then finally, artiodactyls. These are the cloven-hoofed mammals. These would be the ancestors to deer, sheep, cattle, things like that. They appear in modest diversity at mid-latitudes in the early Eocene. No artiodactyls in the Arctic. So there's some weird absences as well. If you compare the Arctic mammals to a very colorful donut over here, which is a locality, one of the more productive localities from the Green River Basin in Wyoming, that's the same age, what you're going to see is lots of horses, fair amount of artiodactyls, Hyopsodus, that weird little archaic ungulate, and then what's really cool is the primates. They do have a lot of primates, but they're completely different families from the primates here. So even though you have primates, both sites, the Arctic is overrun with plagimenids and these paramammiid primates, whereas you have different families at mid-latitudes, which is kind of cool. So we know what's interesting. So even though you're diverse in the Arctic, your composition of your fauna is a little strange. And so the million-dollar question to us became, well, okay, where are these mammals living in the Arctic, and what are they eating? What sorts of things are they eating? I showed you this picture at the beginning, but I don't think I gave you an idea of what these are. Does anybody know what these things are sticking out? Tree trunks, yeah. These are tree trunks from Strathcona Fjord, fossil forest, and it's sitting on a coal seam. If we and the paleobotanists have studied these in detail. If we assume these trees represent one generation of trees, you've got a forest that's as dense as the cypress swamps, probably denser than the cypress swamps in Alabama. I mean, we are dealing with a swampy, rainforest. The precipitation values that the paleobotanists have come out with is about 150 centimeters a year. So this is and most of that water is coming in the summer. They make comparisons to rainforests in Asia today. So you've got a rainforest, basically. These animals are marching around a very dense rainforest. What's interesting, when you start looking at the plants from there, and this is the work of Dave Greenwood, Jim Bassinger, and late Leo Hickey, is that you have some names that we recognize: chestnut, tilia, sycamore. There's some 30 different morphologies of leaves up there, a range of different plants, including this guy, metasequoia, or the Dawn redwood. Most of the tree trunks are thought to belong to Dawn redwood. So you have a lot of different plants. So you can look at fossil plants to get diversity. You can also look at pollen to get diversity. So I've worked with paleobotanists. I've also worked with palynologists. And the next slide I'm going to show you is going to look a little like a rarefaction curve, and I'll show you how to read it, but it was done with a palynologist. And what we know about the pollen in the Arctic, first of all, this is called a species accumulation curve, and you read it from left to right. These are the number of pooled samples, and each sample would be, I believe, a couple hundred grains of pollen are counted per sample. This is a very long, tedious work. I didn't do it. My palynologist did it, Guy Harrington. And then this is the number of taxa, so the number of different kinds of pollen observed. And what you find, this is the Arctic line in gray. A is a southeastern forest, like a swamp forest in Alabama. B is a mixed forest, where you've got mostly deciduous angiosperms, but probably some evergreens. C is a boreal forest, and then finally D is a tundra. If you read this curve, what's called the species accumulation curve, which is going really steep here for the Arctic, it is more comparable to what you'd see in a southeastern forest today and this black line right here, which is the early Eocene western interior, so Wyoming and Colorado, early Eocene. So what this is suggesting, that at least based on pollen, your plants are as diverse as they were in Wyoming at the very same time. So the diversity curve, there is no curve, it's flat for the plants. But here's the caveat with the pollen, is that nearly half of the different pollen morphotypes, which would be equivalent to a species in the fossil record for the pollen folks, nearly half of them don't occur in mid-latitude Europe or North America. So if we go back to this question of why our mammals might be, why our mammal composition, our fauna, is different in the high Arctic than it is at mid-latitudes, I would argue it probably has something to do with the fact that the forests are quite different. At least 50% of those plants in the forest are different kinds of plants that you don't see at mid-latitudes. This is a reconstruction of the Arctic, Eocene Arctic, that was done by the American Museum of Natural History. They produced an exhibit called Extreme Mammals, and they consulted us to find out who should go in there. And of course, Coryphodon made it in. That's my hippo-like guy. I have not sampled that tooth. I don't see my marks on it, so he has not been sampled for isotopes. And then these are little Coryphodons back here. They tend to be interpreted, even though it's an extinct group called the Panodonts, they tend to be interpreted as hippo-like guys. And so you see them floating around, and that's one of my carnivores, probably a Vulpavis, and I showed you one of those teeth earlier. But I guess what I would argue is that your mammals are different, some of them. Coryphodon isn't. He occurs in mid-latitudes too. But a lot of your mammals, all those different kinds of primates and things like that, are different, probably because your forests are quite different in the high Arctic. So I'll just make a couple summary points here. Your mammals are fairly diverse. Your flora is very diverse. There's essentially no difference in diversity from Wyoming to the Arctic in plants. But the differences in the fauna, the composition, particularly absence of horses, artiodactyls, things like that, may well relate to these forests just being not forests that you would see at mid-latitudes with very different kinds of plants. Okay, so I want to talk about the ocean, and this is more recent work for me and some of my students. So we decided, after we had done a fair amount of work on Ellesmere, we laid out the Arctic map, and I said, wow, look at all that Eureka Sound Group rocks, including the Margaret Formation, mapped over here on banks. And in fact, a chunk of Alligators National Park is covered in Margaret Formation Eureka Sound Group. And the pollen that was done by Art Sweet many moons ago would suggest it's the same age. And so we thought, hey, let's go over to Banks Island. And we had visions of finding so many mammals because there's so much rock over here. And we were just so excited. And when we went out there, the picture I showed you earlier of Banks Island in 2004, the July 1st picture where it was snowing and you saw all the tents, that was the weather. I think we had 3 weeks, and I bet 2 weeks and 6 days was probably that kind of weather. It was just unpleasant. We had cold winds off the Beaufort. And what did we bring back that year? We brought back, that year I believe we brought back 6,000 teeth, and then we went up in a subsequent year and brought back some more. So we ended up with 8,000 shark teeth. And for a mammalian paleontologist, shark teeth are not really what we envision finding. And I'm going, what am I going to do? So what I ended up doing was working with, basically, what do you do when you get 8,000 shark teeth? You recruit a student. That's what you do. You recruit a poor hapless grad student to work on sharks. And I did. I brought in a grad student who did, she worked on modern sharks, and she worked specifically on what we call tooth taxa, understanding, basically identifying sharks based on their teeth. And I thought, she is perfect. This is great. So we brought her in to work on these. And she started, didn't take long, this was Aspen. It didn't take her long to realize that in looking at all these shark teeth, they belong to, if you can believe this, over 99% of them belong to 2 genera of sharks. They're sand tiger sharks, Striatolamia and Characterized. And one thing I learned about sharks that I now have a lot more respect for sharks than I did in 2004, and that is that shark teeth exhibit heterodony, not quite the same way mammals do, but what I mean by heterodony is the teeth in the front look different than the teeth on the sides, which look different than the teeth in the back. And so you can tell where a tooth came from in a shark's mouth by looking at the morphology. And these top ones are all from the front. Those are anterior teeth. Those are side teeth, and these short little guys are at the back of a shark's mouth. And so I kind of gained a new appreciation for these guys because they have some similarities, that part at least, with mammals. You can get somewhere by looking at their teeth. Now, so over 99% of them belong to these 2 guys, 2 genera. And the cool thing is we have Characterized with us today. Characterized Taurus is, we use that as a living analog for our Eocene guy. And where these guys live is they live on the eastern seaboard of the United States and several other places. They live here in these blue areas. They prefer warm waters, warm temperate to tropical waters. So this was a little bit more of an indicator that things were perhaps warm up there. We have a few other sharks from the Arctic, including this guy. This is Odontaspis, also a living genus. This one is also another sand tiger. And then this guy is something called Physogaleus, which has been considered to be related to a shark-nosed shark today. And then these weird things down here, this is all one thing, just different views. It's a ray tooth. This is called Myliabatis, and that's a living ray that we have today in tropical and warm temperate waters. And so here we are. We've got 8,000 shark teeth belonging to 5 different genera. That's it. Over 99% of them belong to 2 genera of sand tigers. This is a bit of an unusual fauna. Okay, well, we started wondering what's going on. First of all, we said, well, you know, maybe the ocean isn't as warm as we thought it was. So, but then we started looking at the fossils that we have, and we have a ray tooth. We've got bowfin scales, amid scales, garfish. This is gar, so this is stuff that was probably washed in there into the coastal waters. And then we even found this in these coastal kind of pro-delta waters, an alligator vertebra. And so this was probably washed in. We're not suggesting he was marine necessarily. But in any case, we're seeing fairly warm indicators generally. The other thing that's really interesting is folks have been working in Antarctica in the early Eocene looking at sharks. And the fact of the matter is, Antarctic early Eocene, the shark diversity is considerable compared to here. So we thought, well, it's not simply being at the poles that's leading to this very low diversity. It's got to be something else going on with regard to that Arctic Ocean. And so what did we look at? Let me see if we can, not going. There we go. So what we started looking at then is, well, okay, let's go back and look at the Eocene Arctic Ocean basin. And most reconstructions today are going to give you something along these lines. It's a very closed configuration. You got a very narrow Turgay Strait coming up, but for the most part, your ocean basin is fairly closed. We know this also based on the fossils. We know this, there's been a number of tectonic studies, but also the fossils suggested it early on, in that you have Coryphodons in mid-latitude and high-latitude North America. You've got them in Europe, and you've also got them in Asia. And Coryphodon isn't the only mammal that does this, but you've got several genera in common in the early Eocene among these 3 large continents, suggesting that there was dispersal going on. And if there's dispersal, we had to have land bridges, and that would also suggest our basin should have been quite isolated. So we started thinking, well, okay, you got an Arctic Ocean basin that's isolated. You probably have this intensified hydrologic cycle because you got coal swamps sitting in the Arctic rainforests. Basically, you've got rainforests in the high Arctic at this time, so you've got lots of moisture, lots of water. Malcolm McKenna, the late Malcolm McKenna, said, well, if you've got lots of water basically washing off the continents into a largely isolated Arctic basin, that ought to be brackish. That ought to not be as salty as what it is today. And in fact, Malcolm McKenna called it Lake Arctica. And so we thought, well, okay, let's start looking at salinity, because certainly salinity, reduced salinity, can be a cause for low diversity. You see just a few different kinds of sharks. One of the things that usually comes up with people is they go, well, what's the salinity doing? Because sharks tend to like saline waters. So maybe there's something with the salinity. So we said, well, let's see what we can do in salinity. And I'll just point out a couple more spots here. There has been freshwater fern by the name of azolla, these little spores found in Arctic cores out on this area called Lomonosov Ridge. So they've drilled these cores, and they find these spores that would suggest fresh water. And a couple of authors by the name of Waddell and Moore also sampled fish bone in a core, stuck it into a paleosalinity model that they built, and came up with a reduced salinity, whereas the Arctic salinity today is usually between 31 and 35 PSU, which is just practical salinity unit. You don't need to worry about that. Just 31, think 31, 35. These guys came up with an Arctic Ocean salinity of about 21 to 25. there had been some questions raised because the bone looked a little funky. There were concerns about diagenesis. Was this really right? And so we thought, well, why don't we try this? Why don't we use our sharks and try and go for salinity? And so what we first did is we teamed up with a Dwayne Fox, who's a biologist. And this is what he does for a living. You're going to love this. Well, he should be on TV for this. He works Delaware Bay a lot, and he catches and tags sharks, including sand tigers. That's what he's got there. And while he's doing this, he pulls out a tooth for us. And so what we did is we took that same paleosalinity model, and we sampled our sharks for oxygen, for their geochemistry, their oxygen isotopes. I should have pointed that out, that the paleosalinity model needs isotope data. We sampled our shark teeth, stuck it in their model to see if we could basically come up with the salinity of where these sharks would have been living, the modern ones. So this is a way just to ground truth your model, make sure your model actually works for these critters. And what was kind of cool, what you're looking at here is salinity, PSU, this practical salinity unit, and frequency. And what we found here is that our average salinity of our sand tiger sharks was 34.9, and the average salinity of the water that they were in was about 35. And so we thought, okay, I think this model's going to work. So now what we did is sample the fossil teeth, plug them into that same model, and see what we come up with. And that's what we ended up doing. So what you're looking at here is modern sand tigers. So same guy I'm working on, characterized. This is Lomonosov Ridge data from Waddell and Moore that was published in 2008 based on fish bone. And this is what we come up with on Banks Island. And we basically come up with a salinity of 12.7. Okay? Arctic Ocean is somewhere between 31 and 35. I will add a caveat here. This is the beginning of this kind of work for us, not the end. I wouldn't take that as the final value because what you're dealing with here is coastal waters. And Strialamia and Carcharias today live in coastal waters within a couple hundred meters. So you're probably dealing with shallow coastal water salinity. This is not telling us about depth necessarily. I think ideally you would go for different kinds of shark taxa that we feel comfortable might be living at these different layers, different stratigraphic, stratigraphic layers underwater, but we don't have that yet. So this is probably telling you coastal. It's not telling you fully, but let's face it, 12.7, that could certainly explain why you don't have any diversity. That's a really fairly low salinity. Okay, so summary for this part of the talk, I just want to say that what we find with the Eocene fish fauna off the coast of Banks at least, or shallow coastal waters off Banks, are really low diversity, dominated by these sand tiger sharks. But these coastal waters, at least, were probably fairly brackish. We're fairly confident they're also warm. And this is all fairly consistent with what the paleogeographic reconstructions and tectonics and so forth have said about the Arctic Ocean basin, that you're dealing with a fairly isolated ocean basin, fairly brackish. Okay, well, I want to just summarize this because you guys have been very patient. I just want to, so this is Malcolm McKenna, the late Malcolm McKenna, up in the Arctic in 2001, and that is Fossil Bay in the background. That's on Ellesmere Island, looking for fossils, and that's where we spend most of our time. I just want to say that keeping this in mind, that this is Ellesmere today, and this is Ellesmere 52 to 53 million years ago. That's one of the reasons I study the Arctic. It's just an amazing transformation that we've seen in the last 50 million. I just want to thank these various groups. We've been really lucky in having a lot of support from the Nunavut government in the Northwest Territories, logistical support. Polar Continental Shelf has helped us a lot. I've worked with a lot of colleagues, including Mary Dawson, the late Malcolm McKenna, Jim Bassinger out of Saskatchewan, and Dave Greenwood out of Brandon, the paleobotanists. And then we had funding through both National Science Foundation and the National Geographic Society up there. And then with that, also thank my current lab of students. This is Aspen, the young woman who worked on those shark teeth for me. She did a great job, and this is one of the undergrads I worked with about a year ago, Dina, who looked at shark teeth to estimate body size in the sharks on Banks and also at mid-latitudes, and discovered that they're all not all that different, which is kind of cool. And then this is my current lab of students. I do advise male students. I have had people look at that and go, what's going on? I go, no, I've had a number of male students in my lab too, and they do survive. So everybody makes it. So okay, and I'll just leave it there. This is Clinker Airport. I promised a picture of Clinker, and we called it an airport because we actually had 2 airplanes one year that brought us in. We had a big enough crew, but this is the one where I tell you they land this way, unload us, and then they'll turn around and they'll take off the other way, and there's a cliff at the end, and so they better take off. And so far, so good. So I'll leave it there, and I'll just open it up for questions.